A decision tree is a flowchart, like model that splits data into branches based on feature tests until it lands in a leaf with a prediction. Trees are popular because they're interpretable, handle nonlinear relationships, mix numeric and categorical features, and require little preprocessing. They power ensemble methods like random forests and gradient-boosted trees. But even a single tree is a great place to start. Trees are built top-down. At each node, the algorithm tries every candidate split and chooses the one that most reduces impurity. Without limits, a tree will keep splitting until each leaf is pure, often overfitting. We control complexity with parameters like max_depth or via post-pruning. Each internal node is a yes/no question. Each path from root to leaf is a rule, offering transparency for regulated domains. At a node, suppose the class proportions are p_1, p_2, up to p_k. Gini impurity is calculated as 1 minus the sum of the squared proportions. Its range is from 0 for a pure node to near 0.5 for two classes with a 50-50 mix, representing maximum impurity for binary classification. Gini impurity can be interpreted as the probability that two items drawn at random from the node have different labels. Entropy, from information theory, is an alternative metric calculated as the negative sum of each proportion times its base 2 logarithm. Both metrics rank splits similarly in practice. Gini is slightly faster to compute and is scikit-learn's default. When choosing a split, we compute impurity decrease, which is the parent impurity minus the weighted average of child impurities. The split with the largest impurity decrease wins. For numeric features, trees try thresholds sorted from unique values. For categorical features, we often one-hot encode them. To avoid overfitting, start with shallow trees, typically with a max_depth of 3 to 6, to get readable rules. Use min_samples_leaf, for example, 5 to 20, to avoid tiny, noisy leaves, and prefer class_weight equals balanced for skewed classes. Evaluate with cross-validation and inspect learning curves to see if more data or regularization helps. For production performance, consider ensembles like random forest or XGBoost, which average many trees to reduce variance. Here's a quick, hands-on example using scikit-learn to train a small decision tree on iris data. We load the iris dataset, split it into training and testing sets, and then fit a constrained decision tree classifier. After fitting, we evaluate the model using a confusion matrix and classification report. We can also inspect feature importances, which indicate which splits contributed most to impurity reduction. Finally, we visualize the tree, showing Gini at each node, sample counts, and class distribution. The plotted tree shows Gini at each node, the sample counts, and the class distribution, allowing for human-readable rules. Here's a tiny helper function to manually compute Gini impurity for intuition. For example, a mix of classes like 0, 0, 1, 1, 1 results in a Gini impurity of approximately 0.48. Try computing parent Gini and child genus for a candidate threshold to see the impurity decrease that drives split selection. If your top split is petal length less than or equal to 2.45, it means if petal length is short, predict setosa. Otherwise, the tree goes deeper to separate versicolor versus virginica. Each leaf displays the class distribution and majority class. Common pitfalls include data leakage, unbalanced classes, and too deep trees. You'll see near-perfect training accuracy and poor generalization with overly deep trees, so always regularize. Use a single tree when you need clear rules and explainability for areas like risk assessment or quick prototypes. Use random forest or boosted trees when accuracy and robustness matter more than a single set of rules. A decision tree partitions the feature space into rectangles using greedy impurity reduction. Gini impurity is a fast, effective measure of node purity. Entropy is an alternative with similar behavior. Control complexity with depth and leaf constraints, and validate with proper splits and cross-validation. Start with a small tree to learn the data structure, then move to powerful ensembles for performance at scale. With these ideas and the code template, you can train, visualize, and interpret decision trees, then graduate to powerful ensembles while keeping your models grounded in understandable logic.